Hello everyone, in this video lecture we're going to talk about Solidity. Let's just start diving into it one slide at a time. If I talk about Solidity, since it's a language, let's come to the code layout. It's a smart contract language, I would rather say. So code layout, indentation, please use 4 spaces instead of tab to maintain the indentation level. Avoid mixing your spaces and your tabs. Two blank lines rule, use two blank lines between two contract definitions. One blank line rule, use one blank line between two functions. In case of the declaration only, you need not to use any blank lines. Maximum line length, it is supposed to be 79 characters, the upper limit, so that the readers can parse the code efficiently. Wrapping rules, first argument be in new line without opening parentheses. Use single indent per argument should be the terminating element should be the last one. Source code encoding, UTF-8 or ASCII encoding or ASCII encoding, whatever you call it. Import statements at the start. This we used to do with C++, right? Order of functions should be grouped as per their visibility. So how you're going to group your functions is as per their visibility. Avoid extra white spaces immediately inside the parentheses, brackets, or braces. Control structures, braces should open on same line as declaration. If you're putting if, parentheses, condition, condition close parentheses, brace. Write your code and then in the next line after your code is written, you have to put the closing brace. Makes sense? Function declaration, use the above rule for bases. Always add a visibility label. Visibility label should come first before any custom modifier. What is your visibility label? If it's going to be public, it's going to be not public, that's private, right? Mappings, avoid white spaces while declaring mapping variables. Variable declaration, avoid white spaces again while declaring array variables. String declaration, use double quotes instead of your single quotes to declare a string. Order, elements should be laid out in the following order, that stays pragma, import, interfaces, libraries, and contracts. Again, pragma statements, the top, then your import statements, then your interfaces, then your libraries, and then finally your contract. Within the interfaces, within the libraries, within the contracts, the order should be type declaration, state variable, event, and then finally functions. Naming conventions, contract and library should be named using cap words. If you see cap words, C and W both are in your capitals. Contract and library name should match their file names. In case of multiple contracts, in case of multiple libraries in a file, use the name of the core contract or library. Structure names, use again cap word style, C capital, W capital. Event names, again cap words. Function names used mixed case style. Mixed case style means M is not capital but C is capital. Camel casing. Then same for your local and state variables. Constants, use all capital letters with underscore so that it separates them out. Don't have your variable names and your constants getting mixed out. No. Modifier names, mixed case, enum names, cap words. Now, what is a constructor? A constructor is your optional function because it is optional, because if you don't declare it, the contract is going to assume a default constructor, that is, it's going to consider an empty function in case of constructor. So, constructor is your optional function declared with the constructor keyword. How do I know it's the constructor function? You declare it using the keyword called constructor, which is executed upon contract creation and where you can run your initialization code. Whenever your contract has to run, this is the code that is going to run first, and then your main contract code is going to run. Before the constructor code is executed, state variables are initialized to the specified value if you initialize them in line, or the default value if you do not. Make sense? So before a constructor function, there is another thing that is going to run first, that your variables are going to get initialized to the specified values if you have explicitly mentioned the values, and if you have not explicitly mentioned the values, they're going to get initialized to the default values. After the constructor has run, the final code of the contract is deployed to the blockchain The deployment of the code costs additional gas. Now, what is the gas? Gas is just the fuel that you need to, the fuel that you need to expend as per what your code is. And that is always the amount of gas you're going to use, the amount of things that you're going to put expenditure on is always linear to the length of the code. Makes sense? Now your JSON output. So now let's talk about the storage layout of your smart contract. Now what happens is the storage layout can be requested via the standard JSON interface. Now when you request it, you get a return as JSON object, and what you get as return is two main keys: storage and type. So the storage key contains an array of objects where each object describes how a state variable is stored in memory. For example, in the layout shown, we have a contract named A with a single variable uint x. The JSON output shows details like ASTID, contract, label, offset, slot, and type. Makes sense? Now we have ASTID, which represents the AST node ID. Contract, name of the contract. Label is your variable name. Offset, byte offset within the storage slot. Slot is your storage slot number, which might be a large value and is therefore represented as a string, because we'll be thinking, why is slot represented as a string? Because it might be very large value. And type, which is the reference key to that variable's type information. In the example, you see the type T unit 256 corresponds to an entry in the types object which defines how that data is encoded. For instance, it shows that this variable uses in place encoding has the label uint256 and occupies 32 bytes of storage. So in simple terms, the structure helps us understand how Solidity lays out and represents variables in Ethereum storage, right? So it's through JSON interface that we request for the, storage layout, and what we get back is a JSON object containing two keys, storage and the type. Now coming to the functions. Okay. Solidity allows you to define functions in two ways, inside a contract as well as outside it. Functions that are defined outside a contract, they're called your free functions. Now, the free functions have an implicit internal visibility, meaning their code is included in all the contracts that use them, similarly to how internal library functions we get used, right? Even though these functions are written outside the contract, they still execute in the context of the contract. That means in the context of the contract, they can still do things like call other contracts, send either, even destroy the contract that called them. However, there's one major difference if you just analyze it off. Free functions do not have direct access to your variable this or to your storage variables or to your functions that are not in their scope. Function parameters and return values. So your functions in Solidity take typed parameters as input. And unlike many other languages, they can return multiple values as output. Parameters are declared the same way as variables, and if a parameter isn't used, let's say I've just passed in four parameters arguments, and then I realize that I'm not using the fourth one. So I can just omit the fourth one, go back, omit the fourth one. Make sense? Its name can be omitted. Similarly, return variables are declared after the return keyword using the same syntax. But the number and type of return values must exactly match the declared return variables, possibly after an implicit conversion. So, in short, your Solidity gives you a flexible function system with both free functions. What are free functions? The functions that are declared outside of your, that are declared not internal to your function. Right? I think we're all good with this. And the ability whatever the ability to have it is all in your how can you pass the parameters, what are the return types. And what is different is that you see the statement on the screen, the statement return with the value of v0 v1 going up to vn. This is not something that we use in general programming languages. There's only one return type, right? But here you can have multiple return types. So I think we're done with your two types of functions, the parameters, the return types. Now coming to your pure functions. Functions can be declared pure if they promise that they're not going to read from or they're not going to modify your blockchain state. Then what are these functions going to do? So these functions, let's say, are past the parameters, and then their work is only to work on those parameters. They're not concerned about the blockchain. They're not concerned about the state of the blockchain, what is happening in the blockchain, what variables are there in the blockchain. No, they do not have any concern to deal with it. They are only, they only keep themselves specific to whatever values are passed into them as their arguments. So in simpler terms, if I have to mention, a pure function depends only on its input parameters, nothing else. Makes sense? If I'm passing in the sum function, let's say I declare a function sum with the parameter a and b, and then I ask you to return a plus b, it's a pure function because I did not even care to know what is happening in the blockchain. My only task was to get my input parameters, work on them, and then return. So theoretically, it could be evaluated at compile time just using its inputs and message data without needing any information about the current blockchain. However, there's an interesting point in that even if you're reading from immutable variables, right, that is not a pure function because you're technically, accessing the blockchain state if you're reading from an immutable variable. So apart from directly modifying state variables, Solidity also considers the following actions as reading from the state. What are those actions? Reading from the state variables, accessing address, that is this dot balance or any other addresses balance. Accessing members of block, right? Anything that you do in this way, accessing transaction, accessing message, except message.sig, message.data. Calling any function that's not marked pure, or using inline assembly that involves certain low-level opcodes. So here if you see, your function f is passed two arguments, uint a, uint b, and declared as public and pure. And also mentioned that this function is going to return uint value. Now what are you returning? Return a into b plus 42. It makes it pure function because I did not care to know anything about the blockchain, right? All the data I used was the data that was passed to me. Special functions, we have some special functions as well. We have first function that is special as receive ether function, right? A contract can have only one receive function and it's declared using the using the syntax as, do you remember? Receive, parenthesis, parenthesis, external payable braces. Notice that it doesn't use the keyword function, right? In other functions, we use the keyword that is function, but here we are not using it. This function is quite restricted. It cannot take any arguments, cannot return anything, and must have external visibility along with payable state mutability. Makes sense? External visibility along with payable state mutability. It can, however, be virtual. It could be overridden, or it could have modifiers, just like any other function. The receive function is executed when the contract is called with empty call data. In other words, when ether is sent to the contract without any function call data attached, we make use of the function receive because receive is payable. Now, if receive is not present, it should have, something like any fallback function. That if there is not a receive function, there is a fallback function, but that fallback function also has to be payable. Else what? Else you're going to throw an exception. So whenever someone sends either directly, for example, using send function, using transfer function, this is the function that particular gets triggered. And if the contract doesn't have a receive function nor a payable fallback function, then any attempt to send ether to that contract through a regular transaction will simply fail and throw an exception. Right? So in short, the receive function acts as the default entry point for direct ether transfers, ensuring the contract can safely explicitly handle all the incoming payments. Now let's come to the fallback function. Fallback function is your special function available to a contract. It has the following features that say it is called when a non-existent function is called on the contract. Like if there is no function, but I'm still making a call to that function, where will my code go? Where will my action point go? My action point is going to call the fallback function, because that is the place where you can fall back to. You don't have anything, okay, fall back to me, right? It is required to be marked external. It has no name, it has no arguments, it cannot return anything. It can be defined one per contract. If not marked payable, it will throw exception if contract receives plain ether without data. I hope this is right with all of you out there. So in first contract, test contract, we have the function, the fallback function, that is assigning x as value 1. And then we have another contract, sync contract, where the function, where your fallback function is external. External, it always has to be external, the fallback function. But here it is also marked as payable function. And hence now your contract, the sync contract, can receive ether. Libraries are very similar to contracts but are mainly intended for the use purpose. A library contains functions which other contracts can call also. Following are your key characteristic of a Solidity library. Library functions can be called directly if they do not modify the state. That means pure or view functions only can be called from outside the library. Library cannot be destroyed because it is assumed to be stateless. Cannot have state variables, cannot inherit any element, cannot be inherited. Now, if I talk about using for, it is A for B directive, right? Which is a very, very handy feature. Why? Now you will understand about this right now. This directive allows us to attach library functions as member functions to any data type. So when I'm going to say A for B, it means all functions from library B can be called as if they were functions of type B. These functions automatically receive the object they are called on as their first parameter. The directive can be used at different levels. At the file level, if I talk, where B must be an explicit type like uint, or inside a contract if I'm talking, where you can even write while using L for star. If I say L for star, what does that mean? That means all functions of library L will be available for all data types in that contract, because star stands for all. So in simple terms, libraries make Solidity code more modular, more efficient, more maintainable. While using A for B gives you the power to call library functions as if they were native methods of your types. Now your error handling. Error handling, this is too much theoretical. So let's just go through what it is written. Solidity provides various functions for error handling. Given, generally when an error occurs, the state is reverted back to its original state, which makes sense, right? If there's an error in between, now I cannot execute this code, so I should revert to the state from where I started. Other checks are to prevent unauthorized code access, right? Following are some of the important methods used in error handling. Started with first, that says assert. Assert, and in the parenthesis we have a bool condition. In case condition is not met, this method call causes an invalid opcode and any changes done to the state to get reverted. This method is to be used for internal errors. Require bool condition. In case condition is not met, this method call reverts to the original state. This method is to be used for errors in inputs or external components. Require bool condition string memory message. In case condition is not met, this method called reverse to the original state. This method is to be used for errors in inputs or external components. Everything same. It provides an option to provide a custom message, right? Just this line of change. Revert. This method aborts the execution and revert any changes done to the state. Revert with the string memory reason. This method aborts the execution and revert any changes done to the state. It provides an option to provide a custom message. Use cases with this is the last slide of your this video lecture, use cases of Solidity. Now, if you have any concerns, if you think there were some things rushed through, or you want some reclarifying videos, you want some concepts to be reclarified, please make use of your comment section. Please make use of the G forms attached. And if you were able to extract a lot of the video, or let's say not a very much, not a great deal of information out of the video, but still you were able to get through the video, the video seemed to like help you out with some puddle or some field to help you out for your semester exams, just go in, like the video, and subscribe to the channel. With this, your use cases of Solidity. Voting. Currently, your voting is dealing with numerous issues, including manipulation of data, fake voters, alteration in voting machines, and booth capturing. Solidity smart contracts can be created and deployed to make the voting process transparent and streamlined. Blind auctions. So in an open auction, individuals can view each other's bid, and that just goes on, and we have disputes, we have frauds. So using Solidity smart contracts, the blind auction can be decided where users cannot see what someone bid until it ends. Crowdfunding. Crowdfunding done via smart contracts can solve issues like the commission of a third party and management of data. Solidity smart contracts for crowdfunding do not require centralized systems to build trust, thereby reducing additional costs. So with this, I believe we are done with this lecture. Thank you so much. Bye bye.